Hello, my name is Andrew Richards. I'm the founder and CEO of Codeplay, a company based here in Edinburgh, in Scotland. I'm going to talk today a little bit about who we are, and then what I'm going to talk about is the business of AI accelerators. So this talk really is about RISC V in the context of using it to accelerate AI applications, particularly accelerators attached to other systems, ARM CPUs, Intel CPUs, that kind of thing. And there's a lot of challenges in selling AI accelerators in the market. And I'm going to talk about how RISC V solves that challenge. It makes a lot of the problems go away. And I'm going to talk about how Codeplay helps. So first off, if you haven't heard of Codeplay, we get design wins for accelerator vendors. Really, we're programming models people, but if you want to get a design win for your accelerator, then you need programming models in order to get the software onto the device. You need a programming model. And so that's what we do. We work with people like US national labs and standards bodies and Intel in order to get this big design win for the Aurora supercomputer, which is hopefully the world's first exascale supercomputer when it arrives. And also we work with Renesas and their RCAR platform, where they do an AI processing system for driving a car. So let's start with the market. So who would want these accelerators for AI? So there's a huge market for AI accelerators. There's people who want to accelerate AI. There's lots of use cases for it. But currently it's massively dominated by GPUs from one vendor. So if we want to build a chip that's going to take a portion of this market, first we need to understand the market and the customers, what they want. And then we need to define a product that customers will buy. And then we need to build that product. So I'm going to rush through quite a big process. So if you look at this AI accelerator market, what is it? So people often talk about ResNet 50, for example. That's common neural network people use about. What it does is you give it a picture of a dog and it tells you it's a dog, basically. So let's ask the question, is there a market for something that, like ResNet accelerator? So Facebook users uploaded 350 million photos a day. That's in 2013. It's probably more than now, but you know, how much more is it really? According to the latest MLPerf results, a single Intel Xeon CPU can do over 345 million ResNet 50 classifications per day. So therefore, the market for accelerators doing ResNet 50 in hyperscale data centers is less than 10. So ResNet 50 is not the application that people want to use when they want to accelerate their AI. There's something else. We need to ignore ResNet 50 to find the market. So let's look at what it really is. So there's two approaches to building accelerators. There's vertical versus horizontal acceleration. So if we have an AI model, we can analyze that algorithm for performance requirements. And then we can design a combined software and hardware solution that will achieve very high performance on that algorithm. And this is called vertical integration. It kind of goes vertical, although well, I wiggled it a bit, but it gives you very high efficiency, but quite a long time from algorithm to market. So the alternative is you've got researchers designing AI models, and there's an interface specification to people developing on an AI dev kit. And then what happens is those researchers continue to develop AI models, and people continue to do performance analysis independently. And so what happens is you're able to accelerate future AI. So by the time your accelerator comes to market, you're able to accelerate the new AI models. And this is called horizontal integration. And the advantage of this is it gets you very high performance on the latest AI algorithms. The problem with it is it requires a more complex organization because you're supporting people developing software. So therefore, it becomes very important to be able to have tools in order to be able to develop the software. And there's a long time while you're designing your processor where the software changes, but you're able to support that software. So it's a more complicated thing to do. So let's have a look at which fits the market. So we know that GPUs are hugely successful. I mean, the latest figures I got was $3.7 billion in AI and HPC accelerators. And there's this huge CUDA ecosystem of AI and HPC software. And then we have vertical solutions, which interestingly, they actually sell less, right? They sell a few $100 million. You can kind of work out how much they sell from some of their market reports and things. It's not always easy, but you get an idea. So it's quite a lot less that they sell, but it's still, you know, it's a real business, but they need to be able to design both the software and the chip to make this work, right? These people are AI software experts, and they're able to design a chip for their software. And then there's lots of intermediate implementations. So there's AI graph accelerators that are kind of neither horizontal nor vertical. They're not a platform because you can't just go off and develop software for them. You can maybe take a graph, but that's not really the same as developing software. But they're not full application because they're not designed by people who actually have an application. And the market for that is tiny. It's the order of a few tens of millions of dollars a year. And it's divided between hundreds of competitors. So from a business point of view, this is absolutely the partial horizontal vertical is completely the wrong way to go. So let's have a look at RISC V. It's kind of changes things a bit, actually, if we think about some of the problems that we were talking about before, because RISC V is a well-defined platform. So actually, there is already an organization that enables people to develop RISC V. So that's kind of interesting. And that means we can reuse existing compiler technologies. We don't need to develop a compiler technology for each processor because we can just reuse the technologies that are already there. We just adapt them for the different variations. Now, what's missing is the offloading model supported by GPU. So a GPU goes from a host PC or an ARM processor onto an accelerator that could be multiple RISC V cores, for example. But there are standard programming models that provide this offload model. That OpenCL, Vulkan, and SYCL is one that I've been very involved in. So there are already solutions to this problem. So that means designers can take these RISC V cores and they can customize them for their applications. So they can customize the vector widths and they can add extra instructions for certain use cases, and they can adapt the memory systems. You know, whether you've got on-chip memory or off-chip memory or cached memory or uncached memory. You don't need cache coherency for a lot of these standards. And actually, these offload programming models like OpenCL and Vulkan and SYCL adapt to different vector widths and different instructions and different memory systems. So you can write the software once, and you can find out. You can customize your RISC V core or lots of RISC V cores, and you can customize the memory system, and you can find out what's best for your application. And you can then run lots of software on it. So actually, I think this is actually a game changer, really, for the AI accelerator market. It really changes things because it just makes it so much easier for people to customize the architecture. Now, if you wanted to look into the technology, I've managed to put all of the technology on one slide. But basically, what I'm trying to show you here is a quick summary of how a GPU piece of software maps to a bunch of cores on a system. So it starts at the top here. Somebody might write code in OpenCL or SYCL or CUDA, and they'll write it as scalar code. So they'll write these scalar operations. And what happens on a GPU is you pretend that you've got thousands of threads. You haven't really got thousands of threads. You've got these SIMD cores and stuff that you duplicating it across all of your SIMD lanes and all of your multiple cores using a technique called whole function vectorization. It's got lots of different names, but we use the term whole function vectorization because that's where the paper, that's the paper that we use to be able to describe that as the source for all of this. But you know, it's single program, multiple data, and single instruction, multiple threads, and all sorts of things like that. But whole function vectorization is the act of transforming that GPU-style code into something that runs on multiple SIMD cores. And then in OpenCL, we have these address spaces which can map to on-chip SRAMs or tightly coupled memories, or whatever you call it. So there's, if you lay out your chip with these on-chip SRAMs that aren't cache coherent or don't have caches or whatever it is, then actually they map very well. And the RBV intrinsics actually support whole function vectorization really, really well. And then we have things, if you've got a large on-chip buffer, we can support that. And then you might have fixed function units as well. You might put some other thing that does a matrix multiply or something, and that would be an extension to OpenCL, but there's standard extensions for that called built-in kernels. And you might have a control core to control it all, and that is where we put the command queues in OpenCL SYCL terms. And then that always goes down to an accelerator, and then you'd have high bandwidth memory where you would store the buffers, and then DMA, and there's stuff in OpenCL and SYCL to be able to do DMA across the host PCI Express, and then there's offloading from the host CPU. So if you design your hardware like this, then actually the OpenCL or SYCL model works very well. Actually, maps very well to it, and you can adapt your processor core to find out what fits your application. So at Codeplay, we have two products. One's called Compute Auto, and that gives you the Vulkan, OpenCL, and SPIR standards, or SPIR V standards. And we see that as a lower level thing. Gives you a high level of programmability, and it also it's really useful actually for doing graph compilers. A lot of people are quite dismissive about OpenCL, like it doesn't have a lot of adoption, but it actually does. It's underneath the hood in a lot of systems, particularly AI graph compilers. So there's a lot of graph compilers like Glow and Halide and TVM and CloudML and OpenVINO to some extent use OpenCL underneath. So you can actually run a lot of software. A lot of AI software and machine vision software as well. So if you want to do machine vision and deep learning, which is really common, you can run OpenCV, and all of that runs on our Compute Auto product. And we've ported that to RISC V, so just out of the box it works, and you can configure it for the details of your RISC V core, and you can use the vector intrinsics and DMA system and stuff like that. And then if developers are using CUDA, we worked on defining the SYCL standard. We're the leaders of the SYCL standard, but it's an industry standard that's used by people in like Intel for their one API system. That's going into lots of high performance supercomputers and things. It's very easy to port from CUDA to SYCL, so there's lots of software that runs on top of SYCL. And we provide Compute CPP as our implementation of SYCL, which sits on top of that, but uses special features for different bits of hardware. So basically, out of the box, you can get quite a lot of software running on your RISC V cores and then tune the cores for the range of applications. You may think, oh, I want to run full AI applications. And what you find is there are lots of graph compilers out there that will take AI and stuff. I think some of this data is a little bit out of date. I need to update it a bit. But this graph shows you that typical AI graph compilers are of the order of tens of operations. Google's XLA is probably a bit more than that today, but that's close to, that's much more like hundreds of operations. Whereas if you look at CUDA and SYCL inside TensorFlow, it is hundreds of operations. So there's about, the summary of this graph, even if we update it today, is that there's tens of times more operators supported if you can support the CUDA or SYCL code. And the reason that SYCL supports so much is because the SYCL code is so similar. The SYCL standard is so similar to CUDA, we can actually support both of them with the same code. It's actually the same code. It's just we've tuned it a little bit. We've removed some of the CUDA things and put in the SYCL things, but it's all in header files, so you hardly ever see any of it. So that's why we're able to just support hundreds of operations, and therefore you can run very advanced AI. So if you want to know what we do as a business, we split our business into three components. So we do silicon enablement. We can build OpenCL, Vulkan, and SYCL for various processors, and we can build compilers and things, and processor-specific drivers and profilers and debuggers. But the great thing about RISC V is we can just license your pre-built implementation of it. And we can work with LLVM, and we are working with LLVM. You'll see us doing some work in the open source LLVM, making sure all of that works together. So we can license you OpenCL, Vulkan, and SYCL, all for RISC V cores. But we also do a lot of open source work. We work a lot in the ecosystem, moving code across from CUDA to SYCL, so people can easily move away from NVIDIA GPUs to open industry standards. We've also worked with Intel actually to have an open source version of SYCL, or one API. Basically, we ported one API to NVIDIA GPUs. That's all open source, so people can use all of that stuff on NVIDIA GPUs today, and then they can switch to RISC V accelerators whenever it's convenient for them. And we develop a lot of open source software that supports all of this stuff. And lastly, for people who want to be able to put this into a card, there's a lot of safety considerations to do with AI. There's quite a lot of complicated things we need to think about in terms of safety. So we're working through all of those safety classifications, ISO numbers 16949 and 26262, and we're working within the MISRA standards body and stuff like that to be able to support all of the different safety requirements that exist for putting it in a car. And that's it. Thank you very much for listening to my short talk today. I hope that after this recording, I'll be online and be able to answer your questions. Very interested to hear what you have to say.